Okay, moving on with our practice exam here. Sliding on to the next page and problem number 5. We have another gas law problem here, although this one's a little different in terms of setup and is a little different in terms of the way you think about it, but I think it's an important example of maybe recognizing some of the relationships we should be recognizing. So we've got a mixture. Here, there's 8 grams of CH4, which is methane, 8 grams of xenon, placed in a container, and the total pressure is found to be 0.44 atmospheres. We're asked to find the partial pressure of methane. Now, we might think, often when we are looking at something like finding pressure, we would consider the other variables that fall into the ideal gas equation, like the temperature and the volume. We don't have any of that here. All we have are masses, and then we have the total pressure. So what's important to recognize about this problem is that if we think about our relationships here, PV equals nRT, moles is on one side of the equation and pressure is on the other side of the equation. And that means that the pressure is directly related to how many moles are present of a gas. Right? If we keep the temperature and the volume the same, the moles goes up, the pressure is going to go up. So in this case, right, if we know the masses of our samples, what we could do is figure out what proportion of the moles, or even what portion of the moles, is methane, CH4. And if we know what part of the total moles methane is, that tells us what part of the pressure comes from methane as well. So what we want to do here is take our samples. So we've got 8 grams of methane, and we've got 8 grams of xenon. And my voice might have gotten funny because I was digging around a little bit down here to find my periodic table because I was anticipating needing to do this calculation. Now, methane is 1 carbon and 4 hydrogens. So carbon's 12.01, hydrogen 1.01, so 4 of them is 4.04. So that one I can do in my head. 1 mole of methane would be 16.05 grams of methane. 8, calculator timed out, 8 divided by 16.05. That is 0.4984 moles. Now, we are limited to 2 sig figs here. That'll be worth keeping in mind, but again, I don't want to round too much, so I'm keeping a few extra digits here. Now, the one I definitely need the periodic table for is xenon. Just doesn't come up that often. 1 mole of xenon is 131.29 grams of xenon. So that means in this 8 gram sample, we have 0.0609 moles of xenon. Make sure I keep that in there, moles of what? Now, to figure out, in terms of moles, how much of my sample is methane, what I can do is just a simple ratio. If I take moles of methane and I divide by the total moles in the sample, right, that'll give me the ratio of what portion of the sample is methane in terms of moles. So that's 0.4984 moles of methane, and I'm going to divide that by 0.4984 plus 0.0609, which would be the total number of moles. So 0.4984 divided by, I'm going to use the parentheses on my calculator here, so I can add those numbers on the bottom and have them stay on the bottom while I'm plugging in. And that gives me 89.11. No, sorry. It gives you 0.8911. I was actually changing it to a percent in my head as I was thinking about writing it down, but we don't really want percent here because we want to compare this fractional ratio to the total pressure. So 0.8911 is the portion of the sample that's methane, right? Or 89.11% of the sample is methane. And if it makes up 89.11% of the sample, it's going to make up 89.11% of the pressure. So the partial pressure from methane gas is going to be the total pressure here, which was given in the problem, 0.44 atmospheres, times 0.8911, right? And this we do want to be two significant figures. So take my answer times 0.4, and that would be to 2 sig figs, 0.39 atmospheres. Okay. Now, there is a reason why that ends up on the practice test. I have used this on a test before, but this is maybe a little more abstract than a question that, a question on a test. I really want there to be a direct correlation between the question and what I'm looking at for a grade. This one doesn't quite fall into just using a gas law equation. This one is one where you have to kind of think about your relationships a little more. And while that's certainly important, and I want you to be doing that, it's maybe a little harder to give a direct grade on a test. So I think you should be ready for issues like this, right? But maybe this problem is a little more complicated than the ones I want to put on a test for gas laws. Okay, I think we have time. Oh, bonus question. If this container was a balloon, which gas would escape faster? Here's the relationship to kinetic molecular theory, and in particular, Graham's law of effusion that we talked about. So in Graham's law of effusion, or in the root mean square speed formula, the average speed of the molecule is related to the temperature and the molar mass. Since these are, so it's directly related to the temperature. Temperature goes up, speed goes up. It's inversely related to molar mass. If the molar mass goes up, the speed goes down. Molar mass goes down, speed would go up. So in this case, the lighter molecule is moving faster, is more likely to escape, effuse through the small holes than the heavier molecule. So if this is a balloon, the gas that would escape faster is the lighter one, is the methane. The xenon, being heavier, doesn't move as quickly, doesn't have as high of an average mean speed, so it would be less likely to effuse and to escape from the container. Now, I think we do have time for number 6 here in the same video. Looking at number 6, again, we talked about enthalpy problems and trying to identify what we would do just by the information provided. What I see here is a target equation and then a bank of known equations. This is Hess's law, everyone's favorite type of enthalpy problem. So what I'm trying to do is I'm trying to recreate the target there from the reactions that are given. So I'll start with CH4 in the gas phase, find it here in the bank, right? And then I want to rearrange that equation so that it's on the right side and or I have the right amounts. So I'm going to reverse that equation. I'm going to say methane breaks apart into carbon and 2 hydrogens in the gas phase. And if I reverse the equation, that means the enthalpy would change sign. So the way I'm using it, it's going to be a positive enthalpy. And let me grab one of my other colored pens and just use a little line there to indicate that's one of the things I need to keep to generate my target equation. Okay, the next thing in my target is 4 moles of chlorine, but I see chlorine 2 different places down here. And that makes me a little nervous about which one should I pick and what should I double, what should I change multiples of. So I'm going to come back to chlorine at the end. If there's 4 components here and I do the other 3, that should help me figure out what to do with chlorine, what helps me with the more complicated one. So let's go to carbon tetrachloride here, the one product. Here it is in the table. It's on the right side. It's the right quantity. So I'm going to use that equation just as it is. Carbon solid plus 2 moles of chlorine gas give me carbon tetrachloride gas. And carbon tetrachloride is the one I want in my product. Now we've added another reaction we want as a reactant in our target, the 2 chlorines. So I'm just going to make a note of that as well. Now this reaction was exactly like it was in the bank, so it would still have a negative enthalpy value there in the problem. Okay, and that would leave the other product that I want is HCl, and I want 4 moles of that. So here it is in the table, but it's not the right quantity. It's 2 moles here in this reaction. I want 4 moles. So what I'm going to do is double all the amounts here, and that would be 2 moles of H2 gas reacting with 2 moles of chlorine gas to make 4 moles of HCl, or hydrogen chloride gas. Now, if doing it with the amounts in the table was minus 92.3, if I have twice the amounts, that'll be twice the energy change, so I would multiply that enthalpy by 2 for the way I'm using it in my problem. Now, I added 2 more chlorines, so look at that. The chlorine did work out, right, just by working out the other pieces, and I got my other product. So all the ones that I underlined there are present in the reaction, and they'll be there when I add up all these 3 reactions and see what the net equation is. But what I want to look at is, do the other pieces all cancel out? So I have 1 carbon here as a solid on the reactant side, 1 carbon on the product side. When I add these reactions together, that cancels out. 2 hydrogens in the gas phase on the reactant side and 2 hydrogens in the gas phase on the product side. That also cancels out. But everything else comes down to my combined equation here. 4 moles of chlorine, 1 carbon tetrachloride, and 4 of hydrogen chloride gas. Now, what Hess's law says is if those reactions can be added together to make the target reaction, then the corresponding enthalpies of the reactions we used can add together to make the enthalpy of our target reaction. So I just need to combine these enthalpies, right? And that's one of the reasons why I think it's important to make sure you account for doubling your quantities, cutting your quantities in half, changing direction, right? And I like to put a plus sign instead of just leaving off the minus sign, just for clarity, because we need to get all those pieces right when we combine them here at the end. So 74.6 minus 95.7 minus 92.3 minus 92.3. So this comes out to be negative 205.7. So the enthalpy change here for this reaction would be minus 205.7. And enthalpy is always in kilojoules, right? And it's always related to how many moles are present in the balanced equation. So sometimes you put per mole based on the reaction, or you could put per mole, but kilojoules is kind of the normal way to describe it once you've learned what the definition is. So this is an exothermic reaction. Because it's a negative value, heat would be released if we did this reaction. Okay, I probably have made it clear if you've watched the lectures or if you've been coming to in-person lectures. I like Hess's law. The odds of there not being a Hess's law problem on the test are pretty slim, so you definitely want to be prepared to take on a Hess's law problem on the test. Okay, that's good length for this video. We'll pick up on the next page in the next video.